In this lecture, we're going to talk about solving inequalities in two variables with an end goal of building up to systems of inequalities. Let's first talk about what it means to find a solution to an inequality in two variables. A solution to an inequality in two variables is a pair of inputs for those variables which makes the statement true. So similar to the solution to an equation, a solution to an inequality is just a set of inputs for the variables that make the statement true. We're typically going to deal with the variables x and y, and if the variables are x and y, and the statement is true when x equals a and y equals b, it's customary to write the solution as the ordered pair a comma b. And when we say the ordered pair a comma b is a solution, we mean plugging a in for x and b in for y makes the statement true. To make sure that we have a handle on this definition, let's look at a specific inequality and test some ordered pairs to see if they're solutions. In this example, we're told to determine if the given ordered pairs are solutions to the inequality x squared plus y is greater than 2. The first ordered pair we're going to check is 0, 1. To see if 0, 1 is a solution, we're going to plug 0 in for x, we're going to plug 1 in for y, and we're going to ask if that leads to a true statement or not. Is 0 squared plus 1 really greater than 2? Well, 0 squared plus 1 is 0 plus 1, and 0 plus 1 is only 1, and 1 is not greater than 2. This is a false statement. So the first ordered pair is not a solution. 0, 1 does not make the statement true. Next we have 3, negative 2. So I plug 3 in for x, I plug negative 2 in for y, and I ask if this is greater than 2. So that's 9 minus 2. And 9 minus 2 is 7. And 7 is greater than 2. This is true. Because this is true, that means that 3, negative 2 is a solution. What about negative 1, 1? Let's see, negative 1 in for x, 1 in for y. Is that greater than 2? Well, that's 1 plus 1. And the statement we get is 2 is greater than 2. And that's false. No number is greater than itself. If the inequality hadn't been a strict inequality and said greater than or equal to, then this would be a true statement. But 2 is not bigger than itself. This is not a solution. It's only a solution if the statement is true when you plug in the inputs. Now, 3, negative 2 is a solution. We verified that, but I hope you can see it's not the only solution. You could probably guess lots of ordered pairs that are going to work. 3, negative 2 isn't the only one. If we want to give the solution to an inequality like this, we need a way to display all of the ordered pairs that make the statement true. You can't possibly list them, there are infinitely many of them, and we can't use anything like interval notation to do this because we have 2 coordinates. So the way we typically do this is to draw a graph. Here's the process. If you want to sketch the graph of an inequality in two variables, the first thing you do is you replace the inequality symbol with an equal sign and create a boundary by graphing the resulting equation. When you change the inequality to an equal sign, you've now got an equation that you can graph. We know how to graph lots of different equations in two variables. If the inequality is not strict and has a greater than or equal to or a less than or equal to, you draw a solid boundary, so a solid line or a solid curve. Draw a solid boundary if the inequality is greater than or equal to or less than or equal to. We use a dashed boundary if the inequality is strictly greater than or strictly less than. And the convention we're using here is when you use a solid boundary, those points are included in the solution. And when you use a dashed boundary, those are not included in the solution. So after you've drawn this boundary line, you've basically divided the xy plane into two regions. So you select a test point on either side of the boundary, one of those two regions. You do not pick a point on the boundary. You pick a point in one of the regions determined by that boundary. If the test point makes the statement true, then we're going to shade in that region of the graph to indicate that the points on that side of the boundary are all solutions. If your test point makes the statement false, then none of the solutions lie in that region and you have to look in another region. So we were looking at the inequality x squared plus y is greater than 2, and we found one solution, 3, negative 2, but now we want to sketch the graph of all of the solutions to this inequality. So the first thing we're going to do is graph the equation x squared plus y equals 2. And because this is a strict inequality, we're going to do that with dashes. Now at first glance you might not know what x squared plus y equals 2 looks like, but if we do a little bit of algebra you might be a little more comfortable. Let me subtract x squared from both sides. we get y equals the negation of x squared plus 2, and now we can do this with transformations. The library function we're graphing is the parabola, y equals x squared, but we're going to reflect that over the x-axis and then shift that up 2 units. That'll put the vertex at 0, 2, and the parabola will open downward, and we want to be careful here to draw a dashed curve, indicating that these are not solutions. Points on the curve do not make the statement true. Any point on the curve would make x squared plus y equal to 2, but we want to know where x squared plus y is greater than 2. So the dashed parabola indicates that the points on the parabola are not solutions. Now we need to try a test point. My favorite test point is 0, 0. As long as 0, 0 isn't on the line or curve, that would be my test point. So I'm going to test 0, 0 in the inequality. You don't want to test it in the equation. We know it's not a solution to the equation. That's why it's not on the parabola. You're testing it in the inequality because that's what we're trying to sketch. So let's see, 0 squared plus 0 is greater than 2. No, that's false. 0 plus 0 is not greater than 2. So 0, 0, which sits kind of inside the parabola, is not a solution, and therefore none of the points in that region are solutions. This means the solutions are going to be on the other side of the parabola, and so we shade that region. So we're shading the region outside of the parabola. We're indicating that any point on the outside, kind of above the parabola, makes the statement true. In particular, I want you to notice that 3, negative 2 is sitting right here, and that was the specific solution that we came up with earlier. We showed that 3, negative 2 was a solution. I also want you to notice that when I said shade, I didn't actually take the time to color it in. This is how a math person shades. You can make it a little thicker if you want. I don't want to see you spending a long time coloring it in. Like if you're drawing on graph paper, I don't want you shading in every single box. I want to verify that with another point. Like we already said 3, negative 2 is a solution and it's outside. But like the point 2, 3 is right here. Note that 2, 3 is a solution because 2 squared plus 3 really is greater than 2. And notice over here we've got like the point negative 4 comma 0. Negative 4 squared plus 0 is greater than 2. And up here we've got 0, 3, let's say. 0 squared plus 3 really is greater than 2. All of the points in the shaded region are solutions. All of the points on the parabola and underneath the parabola are not solutions. So this is how we show the solution to an inequality in two variables. Let's practice this a couple more times before we move on to systems. Let's sketch the graph of the inequality 3x minus 4y is less than or equal to 12. Step 1 is to graph the equation 3x minus 4y equals 12. This is going to create a boundary between the solutions and the non-solutions. Because this is not a strict inequality, because of the or equal to case here, we want to include the points on the boundary, and so we're going to use a solid line. And I guess I just gave that away, but the graph of this is going to be a line. Pause the video and see if you can graph that line. One way to graph this line is to solve for y. You could, for instance, subtract 3x from both sides and then divide by negative 4 and get y equals 3/4 x minus 3. Then you could plot the y-intercept, use the slope to come up with another point, and graph the line. But I don't want you to forget that another way to graph a line is to just come up with any 2 points on the line. And I think a lot of you could probably just guess some points that will work. Like, can you see that when x is 4, y would have to be 0? 3 times 4 would be 12. So the point 4, 0 is on this line. And then if x was 0, y would have to be negative 3, because 0 minus 4 times negative 3 would be 0 plus 12. That's also 12. Those are the exact same points you would come up with if you use the y equals mx plus b form. The y-intercept is 0, negative 3, and then I use the slope. I count up 3 and over 4. If you think it's easier to follow this process and just come up with the y equals mx plus b form, please do that. But if you can just guess 2 points that are on the line, that's often faster. I'm going to draw this with a solid line indicating that the points on the line are solutions. You can see we've now divided the graph into 2 regions. The points above or to the left of the line, and the points below or to the right of the line. We're just going to pick a test point here. I'm going to test the point 0, 0. And I get 3 times 0 minus 4 times 0 is supposed to be less than or equal to 12. Let's see, that's 0 minus 0, that's 0. And yeah, that really is less than 12. That's true. That means that 0, 0 is a solution, and therefore every point in the region containing 0, 0 is a solution. So we're going to take all of these points up here. All of the points kind of above or to the left of the line are solutions, and all of the points below or to the right of the line are not solutions. This sometimes goes against students' intuition because they assume because this is a less than, we're going to shade below. But that rule doesn't always work, and the reason it doesn't work here is because the coefficient on y is negative. Rather than trying to come up with a bunch of rules on when you shade above or below based on the inequality symbol, just pick a test point. The test point method is pretty fast and usually pretty easy, especially when 0, 0 is an option. Let me test another point in the shaded region just to show you that it works. Like I see 2, 5 in that region. So if I plug 2 in for x and 5 in for y, well, yeah, that's going to be true. That's a negative number. 6 minus 20 is definitely less than or equal to positive 12. What about, it looks like 3, 0 is in there. Let's see, 3 times 3 minus 4 times 0. Yeah, that's only 9. That's less than 12. And let me show you that a point on the other side doesn't work. Like for instance, I see 5, negative 4. Let's test 5, negative 4. So 3 times 5 minus 4 times negative 4. That's supposed to be less than or equal to 12. Well, that's 15 plus 16. That's not less than or equal to 12. That's false. And it shouldn't work because it's not in the shaded region. Last one before we move on to systems. Sketch the graph of the inequality x squared plus y squared is less than 9. What's the first step? We're going to graph x squared plus y squared equals 9, and because this is a strict inequality, we're going to use a dashed curve. Here we've got this in the standard form that we're accustomed to for this type of graph. X squared plus y squared equals 9 is a circle centered about the origin with radius 3, not 9. Remember that the right side is the square of the radius. So we're going to draw a dashed circle of radius 3 centered about the origin. My circle got pretty bad on the left side, but remember, it's just a sketch. As much as I want to fix it, I'm not going to. Now we're going to test a point. 0, 0 is not on the circle, so that's what I'm going to test. So I'm going to test 0, 0 in the inequality. You can pick any point you want as long as it's not on the circle. I like 0, 0 because plugging 0 in for each of the variables is typically very easy. So I get 0 squared plus 0 squared is supposed to be less than 9, and yeah, that's true, 0 is less than 9. So 0, 0 is a solution, and therefore every point in that region, which is the inside of the circle, is a solution. Any point inside the circle makes the statement true. Any point on the circle or outside of the circle will make the statement false. I encourage you to test that with some other points, but I'm not going to do that in the video. We're going to move on to systems of inequalities. A solution to a system of inequalities is a collection of inputs for the variables which make every statement in the system true. What's important here is that you have to make sure that every inequality in the system is true. Well, how are we going to come up with that solution set? Well, what we're going to do is we're going to find the solution to each individual inequality and then just find the overlap in where we've shaded. The solutions to a system of inequalities in two variables will be the ordered pairs which correspond to points in any region shared by the graphs of all inequalities in the system. So we're going to find the solution to each individual inequality and just look for where those solutions overlap. That region will be the solution to the system. Here's a simple example of that. We're going to sketch the graph of the system x is less than 3 and y is greater than or equal to 2. So we're going to handle each inequality individually. Let's start with x is less than 3. First, we're going to graph x equals 3 with a dashed line. X equals 3 is a vertical line whose x-coordinates are all 3. And now I guess we can test a point. I mean, if x is less than 3, you can probably guess which side we're going to shade. But just to stay consistent, I'm going to test 0, 0 in the inequality. I get 0 is less than 3, that's true. And so 0, 0 sits to the left of that line, so we're going to shade to the left side of that line. So there are all of the points where x is less than 3. Now I'm also going to graph y is greater than or equal to 2 on the same set of axes. So first I'm going to graph y equals 2, and this time I'm going to use a solid line. Y equals 2 is a horizontal line whose y coordinates are all 2, so right about there. And now we'll test a point. 0, 0 is again an option. You can probably guess which side we're going to shade. We get 0 is greater than or equal to 2. That's false. So I don't want to shade in 0, 0. I want to shade in the points in the other region. So that's up here. And you can see in this upper left-hand side, we've got this overlap. Those are the solutions to the system. Now you can tell by the grid lines I've created that that's what I mean to be the solution. But for systems of inequalities, I will often do some extra shading here. So all of the solutions sit up in this kind of upper left-hand quadrant that we've created. And here it's easy to see that that's true because all of those x coordinates are going to be smaller than 3 and all of those y coordinates are going to be bigger than 2. Let's try one with a little more bite to it. In this example, we also have 2 lines, but this time they're not horizontal and vertical, they're going to be slanted. We're going to sketch the graph of the system 4x plus y is greater than negative 1, and x minus y is greater than 0. So starting with 4x plus y is greater than negative 1. We're going to start by graphing 4x plus y equals negative 1, and we're going to use the dashed line. You can guess some points that will work, or you can just solve this for y. This is y equals negative 4x minus 1. So 0, negative 1, and then a slope of negative 4, I'd move down 4 and over 1. And I'm going to draw a dashed line through those 2 points. Now I'm going to test a point, and what am I going to pick? You know I'm picking 0, 0. If I test 0, 0 in that inequality, I get 4 times 0 plus 0 is greater than negative 1. And yeah, that's true. 0 is greater than negative 1. 0, 0 sits to the right or above the line, so I'm shading that right side. The half plane kind of to the right or above the line. Now I do x minus y is greater than 0. First we're going to graph x minus y equals 0, and again we're going to use a dashed line. Adding y to both sides, we get x equals y, which we might write as y equals x just to be more comfortable. Y equals x is a line with slope 1 going through the point 0, 0. And now we're to the step of picking a test point, and I become sad because 0, 0 is not an option here. 0, 0 is on this line. The line went through the point 0, 0. So I have to pick a point that's off the line, and I'd pick something that's obviously off the line, like I'm going to pick 3, 0 here. There's nothing special about 3, 0. I could have picked 1, 0. I could have picked 0, 1. I could have picked any point that isn't on the line. I just want to pick something that's very obviously off the line so I can see where it sits. 3, 0 kind of sits below or to the right of the line. If I test 3, 0 in the inequality, I get 3 minus 0 is supposed to be greater than 0. And yes, that's true. 3 is greater than 0. Since 3, 0 makes the second inequality true, I want to shade all of the points kind of below or to the right of that second line. So that's these. And now you can see the overlap sits down here, kind of on the right side of both lines. To indicate that for sure, I'm just going to shade this in a little bit darker. And there are our solutions. Let me go a little bit deeper with what our shading says here, because we can get a little bit more out of this. The points in this region on the left where we didn't color at all, those make both inequalities false. Those points don't work in either inequality. Like negative 5, 0 doesn't work in either of these. 4 times negative 5 is negative 20. Negative 20 plus 0 is not bigger than negative 1. And negative 5 minus 0 is not bigger than 0. So the points over here don't work in either inequality. The points in this region kind of at the top work in the first inequality, but not in the second. Like you can see 0, 5. 0, 5 makes the first inequality true, but 0 minus 5 is not greater than 0, so it makes the second inequality false. These at the bottom make the second one true, but not the first one true. And the ones that we've shaded in darkest make both true. And those are the ones we're interested in. That's considered to be the solution to the system. Let's hit a couple more examples. Sketch the graph of the system y is greater than or equal to the square of x minus 1, and y is less than the opposite of x plus 3. Let's start with y is greater than or equal to the square of x minus 1. We're going to graph y equals the square of x minus 1 using a solid curve. I hope you recognize what curve that would be. This is going to be a parabola whose vertex is at 1, 0. That minus 1 is going to shift the graph 1 unit to the right, and we get this parabola shifted 1 unit to the right of the origin. That means 0, 0 is in play, which makes me happy. I'm going to test 0, 0 in the inequality. I get 0 is supposed to be greater than or equal to 0 minus 1 squared. That says 0 is greater than or equal to negative 1 squared. 0 is greater than or equal to 1. That's false. So I don't want to include 0, 0. And instead I'm going to include the points inside the parabola between these two branches. So we're in here. I'd like you to graph the second inequality. Pause the video and see if you can come up with the graph of y is less than the opposite of x plus 3. The first thing you do is graph y equals the opposite of x plus 3. And we're going to use a dashed line here. One way to do this is to plot the point 0, 3 and then use the slope of negative 1. Another way to do this is to just come up with 2 points on the line. So if x is 0, y is 3, that's this point right here. And if x is 3, then y will be 0. That's this point right here. And then I just draw a dashed line that cuts through like this. Now I test a point in that inequality. You know what I'm picking. I'm testing 0, 0. It gives me 0 is less than the opposite of 0 plus 3, which says 0 is less than 3, and that's true. 0, 0 sits below or to the left of the line, so my second shading is going to be below or to the left of the line. And the solution is this intersection inside the parabola but below the line, so it's this little wedge-shaped region right here. The solutions just sit in this one little enclosed area. Here's another one. This one's kind of fun. Not real world fun, math fun. Sketch the graph of the system x squared plus y squared is greater than or equal to 1, and x squared plus y squared is less than or equal to 16. So for x squared plus y squared is greater than or equal to 1, we're going to graph x squared plus y squared equals 1 using a solid curve. That's another circle centered about the origin. This time the radius is 1. So we're going to draw a circle of radius 1 centered about the origin. That does not go through the point 0, 0, so that would be my test point. I get 0 squared plus 0 squared is greater than or equal to 1, which says that 0 is greater than or equal to 1, and that's false. So we're shading outside of that circle. All of the points outside of that circle make that statement true. Now we're going to graph x squared plus y squared is less than or equal to 16 on the same set of axes. So first we graph x squared plus y squared equals 16 using a solid curve. You probably know that this is a circle now. What's the radius? It's not 16, it's the square root of 16, it's 4. So we're going to draw a circle of radius 4. This is going to be a disaster, but just pretend this thing I draw is a circle. Test good old 0, 0. That gives me 0 squared plus 0 squared is less than or equal to 16. 0 is less than 16. This is true. So I want to shade everything inside of that circle. And I'm not going to shade everything. I'm just going to shade the overlap. I hope you can see where the overlap is going to be. It's outside of the smaller circle, but inside of the second circle. Our solution set is everything in that donut-shaped region. Like I said, not super fun, but math fun. I want to hit you with one more example, and that's just to do something that has more than 2 inequalities. In the real world, when you have to solve systems of inequalities, there are typically dozens of them to worry about. We're not going to go that hardcore, but let's look at one with 3. We're going to sketch the graph of the system x plus y is less than or equal to 3, x is greater than or equal to 0, and y is greater than or equal to 0. Let's actually start with those last two. I think we can do these with almost no work. X equals 0 is the y-axis. We're going to draw that with a solid line. And we want all of the points where x is greater than or equal to 0. So we're going to the right of that. Now let's shade in y is greater than or equal to 0. Well, y equals 0 is the horizontal axis, the x-axis. And if we're going greater than that, then we're above that. And you can see the intersection is basically just the first quadrant plus these halves of the x and y axes. And now we have to put in x plus y is less than or equal to 3. That's the one I'm going to show my work on. So first I'm going to graph x plus y equals 3 using a solid line. Now we test a point, and you guys know I'm going to test negative 7, 4. Lame math joke, I'm testing 0, 0. 0 plus 0 is less than or equal to 3, yeah, that's true. So I want to shade everything below the line, kind of to the left of the line. And where is our overlap? Well, remember, we have to stay above the x-axis, to the right of the y-axis, and below our slanted line. So that's this little triangular region right here. The solutions to this system are inside and on the triangle. Because we've included all of the boundaries, any point on that triangle is also a solution. So we've done a decent representation of the types of problems that you want to be able to do. You'll definitely want to find some more examples, both of single inequalities and systems of inequalities. Make sure you're reviewing your graphing rules if that felt a little rusty. If there's anything I can help clear up about my examples or the examples you're trying, please don't be afraid to contact me. You can see me in an office hour, or we can do things by email.